Welcome once again. In this video, we'll be doing Chapter 8 on nonlinear regression functions. So far, we've assumed that the relationship between y and x, here's yi and xi, is just a linear function. And so what we want to do in this chapter, because in the world not everything is going to have a linear relationship. We can think of lots of ways in which the relationship between y and x might be nonlinear. We'll have lots of examples coming up. So what we want to do is generalize what we've done so far and allow for nonlinearities between yi and xi in a way that allows us to use the simple regression techniques that we've developed so far. And to do this, we're going to look at two basic ways to add nonlinearities. The first is going to be to add, so the first group will be when the effect of y, the effect on y of a change in x depends upon the value of x. So the effect of class size on test scores might depend upon how big the class is to begin with. So if you reduce a class from 30 to 25 students, that might have a very different effect than if you reduce it from, say, 20 to 15. And so the effect of the change in class size depends upon how big the class size was to begin with. So it depends upon the value of x, where in this case x is STR, student-teacher ratio, or what we've been calling class size. And the second is when the effect on y of a change in, say, x1, I guess I've been using subscripts, x1 depends upon the value of another variable. x2. For instance, it may be that the effect of class size on scores depends upon how many English learners you have in the classroom. So that when you change class size, if you have very few English learners, the effect is different than if you had a whole lot of English learners. So in that case, the effect of STR depends upon the value of some other variable, %EL, whereas in the first case, the effect of STR depended upon the value of STR. So it's a matter of whether the effect, which changes. See, what we're doing here, remember that we have a model, something like score equals beta naught plus beta 1 times STR plus UI. That's our basic model. And we're talking about this coefficient beta 1. Beta 1 is the effect on score of a change in STR. So we want to let this beta 1 either depend upon the value of STR itself or the value of some other variable. And so that slope coefficient changes. And if the slope changes, that's nonlinear. Because on a linear function, the slope's the same everywhere. And we'll see in a second how that works. So let's do the first class of models first, where it just depends upon x, not some other variable, and see how we might begin to get nonlinearities into our model. Okay, I guess I'll do what the book does and start with the test score example to illustrate. And so at the end of Chapter 7, it's not something I covered, but it should have been something you read. Hopefully you did. At the end of Chapter 7, it goes all through the class size example and applies all the things you've learned up to that point. And it's a really good check to see if you understand the thing. So hopefully you read it and convince yourself you do understand things. But we showed at the end of Chapter 7 that family background matters for test scores. And we're going to use it. There they use, I think, the percent qualifying for federal assistance school lunch programs. We're going to use a broader measure in this chapter. We're going to use average income in the district as our measure of family background. So remember, there's 420 districts. The median income, median is half above, half below, is 13,700. That's family income. And it varies from per person in the household, I should have said. So if you have 4 people, it's 4 times that is the median income. And it varies from 5,300 per person to 55,300 per person. So there's a big difference in the income across these districts from 5,300 to 55. The median is 13, so you can see that it's really skewed towards the higher end because the halfway point's not halfway between them. But anyway, those are just some things to, just some characteristics of the data. Now, if you look at, in the book, hopefully you have it with you there, if you look at on page 259 at figure 8.2, and I'm going to exaggerate this in what I draw, they drew a plot of the family income that I just talked about versus test scores. And you can see in the data, and again I'm exaggerating it, that if when you look at the data, you can see pretty clearly that there's a nonlinear effect. And so if we were going to model this with a linear function, we're not going to fit the data very well because the effect is nonlinear. And so putting a linear line through a function that looks like an arch, sort of, is not going to be very, very useful. And notice that the relationship changes. The relationship between income and test scores is different. I mean, the function really looks like it's more like a nonlinear function like that. I didn't draw that very well. But in any case, when you look at the data, it's pretty clear that there's this nonlinear relationship in the data. And you just wouldn't want to try to fit a linear line through that because it's not going to fit very well. A change in income at high income seems to have a less of effect on test scores than the same change of an income if you start with low income. And so increasing income has a bigger effect on test scores when income's already low. This is what this looks like. So it looks like the relationship looks more like that if we were to fit it. But we haven't learned how to fit lines that are nonlinear like that. So how can we handle that? Slope clearly depends upon the value of x. Well, one thing we can do is to add a quadratic term to our model. So let's think of a model where we say score equals beta 0 plus beta 1 times the score in district I is beta 0 plus beta 1 times income, I and C, in district I, plus beta 2 times income squared plus UI. Now, there's no problem with estimating this with the techniques we've had so far because it's still linear in the coefficients, which is all that really matters. But now we've got a nonlinear relationship in the data because we've got this quadratic term. You can just think of this as another variable. Call this W. You're just regressing score on income and W, where W happens to be income squared. Now, there might be collinearity here that you might want to worry about, but in terms of estimating this, it's not going to be problem. And this then will pick up that nonlinearity in the data. And so by adding, and now we could add beta 3 times str and beta 4 times percent English-laden, beta 5 times whatever. I'm leaving those out of the model because I just want to focus on these things on the nonlinear part. But you can imagine those other things are in the model. We'd certainly want to put those in the model in general. So this is going to allow for some sort of nonlinear. Now we don't know what shape it is because we need to know if this is negative, you'll get one shape for your quadratic. If it's positive, you'll get another shape. It depends upon the signs and magnitudes of those coefficients, exactly what it looks like. But if you go ahead and estimate this, you'll get score hat is 607.3 plus 3.85 times income plus minus 0.0423 times income squared. And your standard errors are 0.0048 and 0.27. And over here it's 2.9. Just glancing at those, remember quickly if this is 1.96 bigger than this or 2 bigger, it's going to be significant. In every case, these are going to be significant. We'll actually do a test in a second. But you can just glance at those and see that. When you plot these data, you get exactly the kind of relationship we talked about a second ago. You'll get a line that looks like this if you plot income against score. And the shape comes from this quadratic term, and then the data are scattered around. Again, this is you can see this drawn in the book. And so that by adding this quadratic term, it allows us to model a nonlinear relationship between score and income. Now, one thing you can do is to test if it's nonlinear versus linear. If beta 2 is 0, so the null there is beta 2 equals 0, that's linear. Because if beta 2 is 0, we just have a linear model, it's a straight line, versus beta 2 not 0, which would be nonlinear. If you do the t for that coefficient, I just pointed out that it's pretty obvious that it's significant. 0.0423 actual minus hypothesized 0 over 0.0048. You'll get a t of minus 8.82. That's way bigger than 1.96 in absolute value. And so this is highly significant. And so there really does appear to be a nonlinear relationship between the two. Okay, now let me make some other points about this. When you have a model like this, what we're saying again is that the slope depends upon the value of x, the variable here. What is the slope of this? If we have score here and income here, the slope, if you've had calculus, is d score, d income. We'll do this another way too. But so if you just take that derivative, d score, d income, that's the slope. That's going to equal beta 1 plus 2 beta 2 times income. Since beta 2 is negative, what that says is that as income goes up, the line gets flatter and flatter. And so it's telling us the relationship looks something like that, the kind of relationship that we thought we had, because beta 2 is negative and beta 1 is positive. And so with these models, you can model these nonlinearities, and you can get different types of nonlinearities depending upon the signs of these coefficients. And so what I'm trying to point out here is, yes, the change in score due to a change in income depends upon the initial value of income. And then the book goes out and then the book does this a different way. So what we're trying to show is that the effect of a change in income on score depends upon the initial value of income. And so the book just does two examples. One, let income go up from 10,000 to 11,000. The data are in thousands, and so we're saying from 10 to 11. So the change in y would be beta naught hat plus beta 1 hat. We know what these numbers are, but I want to illustrate what we're doing here. Times 11 plus beta 2 hat times 11 squared. So I'm just plugging in. Remember, our model is y is beta 0 plus beta 1 times income plus beta 2 times income squared. When we've estimated it, it looks like this. And I'm just plugging in 10 or 11 for both of those. I want the change in y due to this, so I need to subtract off minus beta naught hat plus beta 1 hat times 10 plus beta 2 hat times 10 squared. Then we can plug in the numbers that we had. So the change in y is going to be 607.3 plus 3.85 times 11 minus 0.0423 times 11 squared minus, same thing, 607.3 plus 3.8, is it 5? Yeah, 5 times 10 minus 0.0423 times 11 squared. And if you do this, then the change in y is going to be 3.85. Those cancel. You get 3.85 times 11 minus 10, which is 3.85, minus 0.0423 times 11 squared minus 10 squared, 121 minus 100. And that turns out to be 2.96. So the change in y from 10 to 11 gives you 2.96. Now what if we do it from a class or an income of 41,000 to 40? So this says that if we increase income by $1,000 and we start at 10, we'll raise test scores by 2.96. Now let's go from 40 to 41. I got that backwards. You're going to do the same thing. Change in y will be 607.3 plus 3.85 times 41 minus 0.0423 times 41 squared minus 607.3 plus 3.85 times 40 minus 0.0423 times 40 squared. And if you do the math, you'll get the change in y equals 0.42. So when we went from 10 to 11, we got about a 3-point bump in test scores. When we go from 40, I keep writing this backwards, to 41, we get a change of 0.42, about a half a point change, a little less. And so the effect of a change in income on test scores depends upon the level of income. And so one way, it's not the only way we're going to learn, but one way then to allow for these nonlinearities, to allow that slope coefficient, the beta, the effect of in this case, income on test scores. To vary is to add a quadratic term. Okay. This is a little bit tricky, so let's go through it slowly. So the standard errors of the estimated effects. Standard errors are a little more complicated here. The estimated effects is the change in y. It's a little more complicated here because when we increase income, it affects two terms in the regression. So the standard errors we can't just grab from one of the betas because both beta 1 and beta 2 are involved. And so when it's linear, we know how to do this. We talked about that before. It's beta 1 hat. So this is the model. Y0 is beta naught plus beta 1 x, yi, xi plus ui. There's no squared term in there. This is test scores and this is income. In that case, we know that the confidence interval is beta 1 hat plus or minus 1.96 times the standard error of beta 1 hat times the change in x1. This is x1 here. And we learned that before. We did an example of this in a previous chapter. And so we know how to do that. But when we have these nonlinearities, it becomes a little bit more complicated. And so let's try to work that out. So when it's nonlinear, how do you get the confidence interval for a change in x, a change in x? So to illustrate, consider the case where income goes up from 10 to 11. And you can see how to generalize this from 40 to 41 or 26 to 27 or whatever you want to do. And so remember, this was income. That's from 10,000 to 11,000 in the data. If you work this out, remember that y equals beta naught plus beta 1 x plus beta 2 x squared plus u. So that's our model. The estimated change, and then if you estimate it, you'll get this. That's the estimated model. Then the change in y would be beta 1 times 11 minus 10 plus beta 2 times 11 squared minus 10 squared. If that's confusing, remember we said the change in y is beta 0 plus beta 1 times 10, 11, plus beta 2 times 11 squared minus beta 0 plus beta 1 times 10 plus beta 2 times 10 squared. The beta naughts cancel, so this is equal to beta 1 times 11 minus 10 plus beta 2 times 11 squared minus 10 squared. So that's where that formula comes from. So that's the estimated effect. This is beta 1 plus beta. This turns out to be change in y is then beta 1 plus 21 times beta 2 for this particular case. If you did 41 minus 40, this would be a different number because it would be 41 squared minus 40 squared, and I don't know if I can do that one in my head. 40 squared I can do. 41 squared is a little harder, and it's another 82. It might be 82. Let me not guess. Okay. So what we've shown then is that for income going from 10 to 11, the change in y is beta 1 plus 21 beta 2. What is the standard error / confidence interval? Once we have the standard error, we can get the confidence interval. So how can we get the standard error? There's two ways to do it, only one of which I'm going to worry too much about. The standard error, this is y hat, by the way. I think a second ago I put y equals, it should have been y hat when I had the beta 1 hat. I think I erased it, or I'd fix it. The standard error of the change in y hat turns out to be the absolute value of the change in y hat divided by the square root of f, where the f is from a test, the kind of test we learned in the last chapter, that beta 1 plus 21 beta 2 equals 0. So what you would do would be to run the regression, run test scores on income and income squared and a constant, tell the computer to do this test, and then you'd get that f. And then this formula gives you the standard error for the change in y hat. And then from the standard error, you can get the confidence interval. It's a change in y hat plus or minus 1.96 times the standard error of change in y hat. So where does this come from? Where does this formula come from? How do you get that formula? So let's first derive the formula, and then we'll do an example from the test score, surprisingly enough. Bet you couldn't see that example coming. Recall that for q equals 1, one restriction, f equals t squared. So the f statistic is equal to we can do the t for this, beta 1 hat plus 21 beta 2 hat. That's the actual minus the hypothesis over the standard error of beta 1 hat plus 21 beta 2 hat. That's just a t statistic. If we square that t, that gives us an f, right? And this standard error, this thing here, beta 1 hat was 21, that is the change in y hat. Okay. So now I know that the square root of f is beta 1 hat plus 21 beta 2 hat over an absolute value, because we've taken the square root, and this can't be negative, over the standard error of either delta y hat or beta 1 hat plus 21 beta 2 hat. So then, just like we said, the standard error, again, this is delta y hat, of delta y hat, move that over there, is the absolute value of beta 1 hat plus 21 beta 2 hat divided by the square root of f, just what we wrote before. And so this is going to be the basis of a confidence interval for the change in y hat. In the model we've been looking at, the one we wrote down the estimates of a few minutes ago, if you do that test on the computer, the f that you will get is, so this is the actual example. The model test score is beta 0 plus beta 1 times income plus beta 2 times income squared. If you run that, the f for the test that beta 1 plus 21 beta 2 is 0, the f is 299 0.94. And we showed a few minutes ago that beta 1 hat plus 21 beta 2 hat is equal to 2.96. Go back and look. We actually worked out this 2.96 number, and this is delta y hat. Okay, so that's everything we need to get the standard error. So the standard error of delta y hat in this nonlinear model is then 2.96 divided by the square root of 299.94. Technically, that's an absolute value, but since it's positive, it doesn't really matter. And that turns out to be 0.17. So the 95% confidence interval for delta y naught, for the predicted change in y from a change in income from 10,000 to 11,000, is 2.96 plus or minus 1.96 times 0.17, the standard formula. Delta y hat plus or minus 1.96 times the standard error of delta y hat. And so the confidence interval is 2.63 to 3.29. Okay? Now the book goes through a second way of doing this where you transform the model and do something tricky. I find that not as useful as this. So this is, I'm going to leave this as an exercise. It's 8.9 if you want to go through it, but I'm not going to do much with that particular section. So let's generalize this approach a little bit and just say, you know, what are we doing here? What are the steps we're taking? And so on. So a general approach to modeling nonlinearities. One is to identify possible nonlinear relationships. And there's two ways. One is to think about economic theory. This will often tell you that there's nonlinears. For instance, we think that money has a more powerful effect on GDP and employment when the economy is near full employment. When the economy is in a deep recession, we think that a change in the money supply has a much smaller effect on the change in output and employment. And if you're in a liquidity trap, a really deep recession, a zero lower bound situation, it may have hardly any impact on output. We saw massive changes in money supply during the Great Recession. The effect on income was very, very limited. And so often you can just think about economic theory and it will tell you to expect there's a nonlinear relationship in the data. And so your first thing is to just think about economic theory. You can also plot the data. And sometimes those plots of the data will point you to possible nonlinearities as well. But economic theory is your first method of identifying those things. Logic. So once you've figured out there's a nonlinearity, you specify the nonlinear function, like the one we did a few minutes ago, beta 0 plus beta 1x plus beta 2x squared. We'll have other ones. We're going to have logs and other sorts of ways to get nonlinearities into these models. But that was the first. And estimate using OLS. And these nonlinear functions will usually be polynomials. That's what we did a second ago, like x, x squared, x cubed. You'll add those terms, or 1 over x squared, 1 over x cubed. You can add those kinds of terms, and they give you more and more complex nonlinearities depending on how many of these terms that you add. We'll do more of this in a second and talk about how you might want to choose how many of those terms to include, but with these are the main ways of doing it. So mostly we allow for nonlinearities using either logarithmic functions or polynomial functions. Okay, so now we've thought about it. Yes, there are nonlinearities. How do I model it? Logs or quadratics, I make a choice. We'll talk about those choices soon. And the third step is to determine if the nonlinear specification is an improvement. And we'll use T's and F to test. For example, I might have yi is beta 0 plus beta 1 x 1i plus beta 2 x 2i. I'm going to add another term here in a second, plus ui. Here I would just need a t, not x2i, x1i squared. Here a t is all I need. I could use a t-test for beta 2 to determine if there's nonlinearities or not, because if that term's not there, we're back to a linear model. But I might have another term, plus beta 3 times x3, x cubed. So now income is cubed. Now, to test if it's a linear model, the null would be beta 2 equals beta 3 equals 0. The alternative is 1 not 0. And that would be an F test. So it just depends upon how many terms you have, and you can do T's and F's depending. In general, then, we can test for nonlinearities using T's and F's. Okay, 4. Plot the estimated nonlinear function against the data. And I'm just going to say see figures 8.2 and 8.3. You just plot xi and yi. And maybe there's a cubic relationship, so it looks something like this, the data. Then you can see how well your model fits those data by plugging in various x's and predicting what y will be into the model. So I can give it x, and it gives me y once I've estimated the model. And then I can see how well it fits the data. And hopefully, you get a fairly good fit of the nonlinear terms. But this is a check on that. You can look at it visually and get an idea about whether you have a good fit or not. And if you've done all that, yes, there are nonlinearities. Here's how I'm going to measure them. I tested them. They're significant. I checked. The model looks pretty good. Then finally, you can do like we did before. You can estimate the effect on y of a change in x. I'm using the books. I like to say estimate the effect of a change in x on y. The book always says estimate the effect on y of a change in x, which is a bit awkward of an English construction to me, but I'm going with the books. And we did this for the quadratic. That's what we did, the 10 to 11 or the 40 to 41,000. And so, yeah. Okay. Now let's start looking at these a little closer. Sorry, I'm trying to keep an eye on the time here. Let's look at polynomials. And these are probably the most useful when y just depends upon 1x. So in general, yi equals beta naught plus beta 1 xi. I don't have to put 1 because there's only one of them. Plus beta 2 sine x squared plus beta 3 cubed xi plus beta r x to the r power plus ui. And so here we've got potentially a polynomial of degree r. When r equals 2, we call it a quadratic model. When r equals 3, it's cubic. I guess I should have said when r equals 1, it's linear in just that one x. Now you could have other terms in the model. I could have an x2 and x3. But usually you're modeling a relationship between y and xi with these polynomials, and you're just looking at a nonlinear relationship of this form. You don't usually go beyond 3 unless there's really compelling reasons to do so. And I'll talk about that in a second. Let me just talk about it now. No, I'll talk about it in a second. I've got a whole page on that pretty much. But generally, you don't go beyond a cubic, and the reason is you don't want to do something called in-sample overfitting. And I'll come back to that. So you can estimate this with OLS. There's nothing new here in terms of estimation. You just have to use your spreadsheet. You've got a row of y's, a column of y's, a column of x's. You make a new column of squares and cubed and however many you need. Usually, as I said, you don't go beyond cubics. But if you did, you could go all the way up to r. Then you just run the regression of y in a constant x squared, x cubed, and so on. And then those estimates can be OLS. This is just like x1, x2 just happens to be x1 squared, x3, all up to xr, where xr happens to be x to the r power, but it's just another x in the model. Okay, to test for linearity, that's pretty simple. You can probably see what you're going to do. The null is beta 2 equals beta 3 equals all the way out to beta r equals 0. And the alternative is at least 1 is non-zero. And that's going to be an F test because it's multiple. In fact, it's F. The F that you want to use is F of r minus 1 restrictions, and we're going to use a large sample, so we'll have the sample size be infinite. And so there's r minus 1 restrictions because we're not using this one. This is 1. So from 2 to r is r minus 1 restrictions because we're starting, notice we start at beta 2 because we're testing for linearity. Okay? And if you add higher and higher order terms, you can get some really complex nonlinearities. In fact, no matter what your original data look like, they can be very, very odd. Yeah, let me not do that. Whatever shape they are, if you add more and more with a linear, say my data looks something like this. With a linear model, I'm not going to get that close at all because I'm going to have to go right through there. As I add, with a quadratic, not so good. Even a cubic, not so good. But as I add more and more terms, I can get arbitrarily close to this line. So the more quadratic, or the more polynomial terms I add to my model, the better I'm going to fit the actual data. And I could get, by adding really, really high terms, number of terms, I can get really, really close to this thing. And in fact, if you add as many polynomial terms as you have data points, you'll fit the data perfectly. You'd never want to do that. Now, why might we not want to fit the data perfectly? Well, notice the waves in this thing. It tends to go up, but if you were to predict, you'd probably predict it's going to look something like that. If I use this model to predict what's going to happen to x, so suppose I want to know what's going to happen to y if x goes up. If I use this model, my prediction is going to point in that direction. If I use a linear model, it's going to point in that direction. When you fit the data in sample really well, sometimes you fit it so well that you don't predict very well out of sample. If these data are going to actually go like this prediction from the linear model is actually closer than this one from the nonlinear model that's pointing upward at this point. So this saying, oh, we're going up, and if you just kept extrapolating out, oh, we're going to go up and up and up and up and up. That's not very useful. That's not a very good prediction. And the problem is you're paying too much attention to the wiggles inside the data. If I just use a linear model to predict, I might actually get closer on average than I would with this other model. And that's because I'm paying too much attention to all the wiggles and not enough attention to just the main feature of the data. And so if you include too many variables, you can explain the actual sample that you have really, 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 really well, arbitrarily well. But once you pass a certain point, you're paying too much attention to all the little noise. You're actually modeling the noise in the data. And if you model the noise in the data and pick it up in sample and try to explain that, you're going to get really bad out-of-sample predictions. And so having too many quadratic terms can really mess you up when you try to predict out of sample. So how do you know how many? Well, as a general rule, so when the number of polynomial terms goes up, there's more flexibility to fit the data that you have. So a polynomial of degree r can have r minus 1 inflection points or turning points. You're basically adding for more turning points when you add more and more data. When you increase the number of polynomial terms, you get more regressors. And in general, what that means is less precision for the betas. And finally, when R goes up, you risk overfitting. You risk paying too much attention to all the little tiny wiggles inside the data set that you have. And then when you extrapolate those wiggles, which are just noise, as though they were meaningful and try to predict from them, you do very badly out of sample. Another reason why you might have nonlinearities is that you have an omitted variable. So sometimes you look at the data and it looks highly nonlinear. Let's look at y and x together, and there's this big nonlinear relationship. And so you start doing all these polynomial things, but what it's really indicating is that you have a missing variable. So sometimes nonlinearities are diagnostic for a missing variable. And if you include that variable in the model, the nonlinearity goes away. And so one thing you want to do when you detect these nonlinearities is to think hard about whether you have any missing variables from the model. And if you do, throw them in and see if you can eliminate the nonlinear problem. So one procedure for picking the value of R. So you start with an R. Start with biggest R you think is needed. So if you look at the data and it looks like a quadratic, probably need a square term. If you look at the data and it looks like a cubic, you probably need 3 terms. You know, if you've got, you can just count the inflection points. If it looks like you've got 2 inflection points, you probably need a cubic. If it looks like you've got 3 inflection points, you're going to need a 4th order, and so on. But you just have to start with the biggest R you think. And so then you start with yi is beta 0 plus beta 1 x plus beta 2 xi squared plus beta r xi to the r power plus ui. So you start with this big model and you do a t-test here. If it's significant, stop. That's what you need. If it's insignificant, throw out that term, eliminate this, re-estimate the model, and test x r minus 1. Do a t-test there. If that's significant, stop. It belongs in the model. If it's insignificant, throw that out and do a test for the r minus 2 term. You continue until you find a significant t. So you keep throwing out the higher order and getting lower and lower until you find a significant t, or you get down to the basic linear model. Then you're going to stop because there's no nonlinearities. And so you start with a big R and then just start eliminating them one by one, r to r minus 1, r minus 2, until you find a significant relationship. Okay, let's look at the test score example. So let's estimate a cubic. So score hat is beta naught hat 600.1 plus 5.02 times income minus 0.096 times income squared plus 0.0, I need room for standard errors, plus 0.00069 income cubed. So if you estimate a cubic with those data, that's what you get. The standard errors are 5.1, that's clearly significant. 0.71, that's significant. 0.029, that's significant. And 0.00069. This t is 1.97. That's barely significant, but it's significant. And so we want to keep that term in the model. So this is our hypothesized model. Is r equal 2 correct? That's significant because it's greater than 1.96. Barely, but it is, and we have to abide by how the test comes out. That's the whole point. You want a procedure where you can't fudge things afterwards. Say, well, I'm just going to assume this is significant or not, depending on what I want. You can't do that. So we just have to abide by this. So this is significant. This belongs in the model. I think I was pointing here a second ago. It belongs in the model. Okay. What about an F test? What if we test for nonlinearities generally? What if the null is beta 2 equals beta 3 equals 0, H1 is 1, 1, not 0, at least 1. The F is 37.7. It's an F of how many restrictions? 2. 1, 2. This is highly significant. So as a group, those things are significant. Individually, they're significant. This one's significant. And as a group, they're significant as well. And so, yeah, that's what you would do. And then you could plot this against the data. That's done in the book, I believe, to make sure the fit looks right and all those sorts of things. All right. And let's continue with this a little bit. We're almost done with the quadratics. But interpreting the coefficients. They're not slope coefficients anymore. It's more complicated. Why? Let's just look at the cubic case. Beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed plus ui. These aren't slope coefficients anymore. In fact, if you look at the relationship between y and x, it's nonlinear. And in fact, the slope here is dy dx would be beta 1 plus 2 beta 2 plus 3 beta 3, 2 beta 2x, beta 3x squared. And so the slope is going to depend upon which x you start with, and the slope actually varies in a somewhat complex way. It follows that formula. And so the change in test scores due to a change in income is going to depend upon what level of income you have. So to interpret the coefficient, it's best to, so for interpreting the coefficients, it's best to, one, plot against the function against the data. So you can see how that slope varies. So if you plot this function, it looks like this, and the data is in there, around it. You can see that as x goes up, it gets flatter and flatter. And so that gives you some notion of how y varies with x. So we want to know if we change x, how does y change? And we can get a sense of what that looks like by just looking at the plot of the data. And then secondly, do what we did earlier, is you can calculate the change in y due to a change in x for various values of x. That's what we did before when we had the quadratic. This is a cubic model. And we looked at the change in y when x went from 10 to 11 or from 40 to 41. For instance, let me just continue on that second point. You'd want to sort of pick a low x and a high x. You can look at your data. Oh, the min's 5, the max is 55. Let's take one on the lower end, say around 10. Let's take one on the higher end, say around 40, and then evaluate it that way. So what you do here, you say, well, the change in y is, say from 10 to 11. Or whatever your data is, x is whatever it is, but in the income case, the 10. So you say beta 1 plus beta 0 plus beta 1 times 10 plus beta 2 times 10 squared plus beta 3 times 10 cubed minus, this is the estimated change. So now we're using the estimated model, minus, and then the same thing, beta naught hat plus beta 1 hat times 11 plus beta 2 hat. I did this backwards. I'm so sorry. I hope you're writing in pencil. These should be 11. This should be 10. I was doing from 10 to 11. We want to do, yeah. I was doing it backwards. 10 squared plus beta 3 hat 10 cubed. And we just looked at what these betas were. Beta naught hat was 600 point. So this number here is 600.1. Beta 1 hat is 5.02. And so on. Beta 2 was minus 0.096. And this one was 0.00069. And the same numbers down here. So you just plug those numbers in, and you can calculate the change in y. So do it for a low, and then do it also for, like, say, from 40 to 41. Change in y hat similarly. Proceed similarly. You just plug in 41 and 40 instead of 11 and 10. And then you can see how the change in y depends upon the income that you have. And if it's more complex, you might even want to try one in the middle. You know, like 25 to 26 or something like that. And so try a bunch of them, and you can get a good sense of what that slope ought to look like. Okay, well, that is the quadratic part. We still have more to do in this chapter, logarithms and interaction terms. But since this video has already run an hour, and there's probably at least an hour left, I'm going to go ahead and stop this one here, and we'll pick it up with part 2 very soon. Thank you.